Okay, in the last lecture we have started particle kinematics. So, we continue with that lecture. So, if you remember in the last lecture we derived this expression for the acceleration of a particle as d square s by dt square E t cap plus ds by dt square times E n cap divided by r. So, where r or the perhaps r or rho whatever we have taken, okay, this is nothing but the radius of curvature. Okay, and this radius of curvature from the geometry, from your coordinate geometry, you can recall that this can be written as 1 plus dy by dx square 3 to the power 2 divided by d square y by dx square, and this you can, this is the modulus, and you can prove this using calculus also. Okay, and this is very useful results. So, in that context we proceed with our further derivation, which will serve us while we work on attitude dynamics, or if you see once you are putting a satellite, say you have gone into an spacecraft which has a robotic manipulator, and now you want to study the movement of the robotic arms in the space. Okay, so, what kind of equations you are going to use there to study such kind of motion. So, those can be studied using very simple kinematics. Okay, or if the moment of inertia, other things they come into picture, then you have to naturally include the dynamics part also, but the kinematics part you can obviously study from this place, what we are going to study right now. So, it is a part of our particle kinematics. So, first of all we will find a derivation. Last time as I was stating that the rate of change of a vector as observed from an inertial reference frame E 1, E 2, E 3, that is non rotating reference frame, is equal to the rate of change of this vector as observed from the E 1, E 2, E 3 okay, from a moving reference frame, rotating reference frame plus omega cross E. So, in that context we made a reference frame here E 1, E 2, E 3, where the unit vectors along these directions are E 1, E 2 cap and E 3 cap, and then we had a rigid body here, and we fixed a triad of axes termed as E 1, E 2 and E 3. This is the body x, body x is fixed in the body. So, it is rotating along with the body. So, let us say omega is the angular velocity of this body with respect to the inertial reference frame, or okay, small omega or capital omega, whichever notation you want you can keep, and then we can point a vector here. Okay, in this body we can take a vector. So, we will make a separate figure here in this place for that. Let us say this is our E 1, E 2 and E 3, and you have a vector A whose coordinates can be determined in this reference frame. instead of putting here E3, let us make it a little vertical. Okay, so the coordinate of, you can break it here. So, the coordinate here of this can be written as A1, A2, A3. Now, these are the components along E1 direction, E2 direction. Here this will be your A2 and this vertical component A3. So, here some point is there whose radius vector is A, and let us write it as P. If this is a rigid body, so naturally this vector gets fixed. Okay, with respect to E1, E2 and E3. Okay, now we can start writing the equation. Let us say the vector A we define as A1 E1 cap, A2 E2 cap plus A3 E3 cap, where the magnitude of A can be written as A1 square, A2 square times A3 square under root. Now, this vector has been written in terms of the components along the body axis A1, A2 and A3. Equally, this vector if you see from the this inertial reference frame or the non-rotating reference frame, okay, this is the center of mass here. Okay, so, if you see this vector from this place, so you can see it is a component lying along the E1 direction, E2 direction and E3 direction. Naturally, these components will be different. Okay, they will not be same as A1, A2 and A3 written here in this place. And we are using capital notation capital A to indicate differ it from the small a, which is often used for acceleration. Okay, so, our objective is to find that this dA by dt is a rate of change of dA by dt as seen from the E1, E2, E3 reference frame. How does it appear? Okay, so, to start with, we can write this equation as d by dt, and A we can write as A1 E1 cap now. Let us take the derivative of this. Okay, so, this is its derivative, and this derivation we are doing with respect to the E1, E2, E3 reference frame. Now, the quantity which are appearing here dA1 by dt, dA2 by dt and dA3 by dt. So, these are the rate of change of the components A1, A2 and A3 as seen from the reference frame E1, E2 and E3. But as we were discussing in the last class that the rate of change of a scalar as seen from a rotating reference frame. Here we have a rotating reference frame and this scalar is present here. Okay. If say this is a fixed point in the rigid body. So, naturally we can write. So, we take the case 1 here as case 1, point P is fixed in the rigid body. So, if the point P is fixed in the rigid body, so the vector A which is fixed here. So, the components of this in the the body reference frame, it will remain constant, okay, it will not be changing. So, what about the rate of change of these components as seen from the this non-rotating reference frame E1, E2 and E3. So, the last time as per our discussion that the scalar as we see from a rotating reference frame or from a non-rotating reference frame, they their rate of change will remain same. Okay. So, irrespective of temperature. So, if the temperature rise, if temperature is a scalar. So, if you have kept something some crucible in the in a rotating reference frame and you are looking at it. So, the temperature that will be measured there and the rate of the change of temperature, it is basically a scalar. So, it will be same as we see it from the non-rotating reference frame. So, what here we want to state, I want to state here that the rate of a change of a scalar, okay, or the time derivative of a scalar, it is the same irrespective of whether it is the moving reference frame or it is a rotating reference frame or non-rotating reference frame. So, the rotation of the reference frame, it does not affect the scalar and it is a derivative. So, the length of a fan blade, it remains same, okay. And if you contract the length of the blade in the rotating reference frame, which is the fan itself sitting on the fan, okay. If it is contracted, so whatever the rate is of the contraction is there, the same rate will appear also from the non-rotating reference frame. Okay. So, from that point of view, what we have written here, this dA1 by dt, dA2 by dt and dA3 by dt with respect to the E1, E2, E3. So, these are basically the derivatives of the time derivatives of the scalar components, and therefore, they will appear same as you look from the either E1, E2, E3 reference frame or either if you look from the small E1, E2, E3 reference frame, that is the body reference frame. So, in both of them it will remain same, but if the point P is fixed in the rigid body. So, naturally these components dA1 by dt even in the body reference frame, naturally it is a 0 and therefore, this will appear to be the same also with respect to the E1, E2, E3. So, this will also appear to be the 0 from the capital E1, E2, E3, which is a non-rotating reference frame. Okay. So, in that case you can write dA by dt as A1 times d1 cap by dt plus A2 times d2 cap by dt plus A3 times d3 by dt. Now, you need to determine this quantity d1 by dt, d2 by dt, d3 by dt. So, we have done earlier this exercise also. So, if this is the unit vector at time t and this is the unit vector at time t plus dt, this angle is d theta. Okay, so, you look from this figure, here this is a vector E1, this is the vector E2 and this is the vector E3. the rotation of this vector, it will depend on rotation of this vector in this plane, and in this plane it will depend on the rotation. Rotation of this vector will depend on rotation around this x, and rotation around this x will affect in this plane. Okay. So, in this plane this rotation will affect in this plane. In this plane we have this rotation is affecting, in this plane this rotation is affecting. Okay. So, these two rotations can be corroborated. Okay. Now, we need to work out all of them. Okay. So, if we say that this is the rotation about this x, the component of omega vector about this is omega 1, about this x this is omega 2, and about this x this is omega 3. So, the rotational rate of this, now we start, and let us put this as the something. Okay, we write it as d theta only. Okay, so, the change is delta E t. Okay, and this change you can write as E 1 cap magnitude times d theta. Okay. And so, therefore, delta E by delta t in the limit, we can write here limit delta t tends to 0, delta E by delta t, this we can write as, let us first take the magnitude, okay, and thereafter we will take the direction part. So, d by dt will be equal to magnitude of E 1 cap times d theta or delta theta by delta t. Okay, so, here we can show this as the delta theta instead of delta t to be consistent. Okay. And this quantity is nothing but equal to 1. So, this gets reduced to theta dot. Okay. So, theta dot is nothing but here omega 3 here in this place, and omega 3, because this is rotating like this, if this vector is rotating like this. So, we will write this as the omega 3. Now, in which direction this vector will change. So, the change vector will be as this delta theta becomes smaller and smaller, this will be perpendicular to this E 1 vector. So, this is pointing in this omega 3 direction. Now, similarly, E 1 can, because this x is also rotating. So, E 1 is also rotating about this x, and for the positive rotation we are giving the taking the right hand rule. So, this is rotating anti-clockwise here, and about the x 1 x also E 1 x we are giving the anti-clockwise rotation. Similarly, about the E 2 x we give the anti-clockwise rotation. So, if the rotation is given about this, so E 1 will shift from this place to this place downward direction. Okay. So, similarly, we need to work out for this, and the net change then will be combination of these two. So, overall this dA by dt, this can be written as omega cross A, okay, where I break up this part, and then we will come to this to show you what exactly has happened. Omega 1 times E 1 cap, omega 2 times E 2 cap plus omega 3 times E 3 cap, and cross E 3 times E 3 cap. So, if you break it up taking the cross product, so you can write it in this way: E 1 E 2 E3 and omega 1, omega 2, omega 3, A1, A2, A3. Take the determinant of this, and this will yield you E1 cap times omega 2 A3 minus A2 times omega 3, okay, plus E2 cap times A1 omega 3 minus omega 1 A3 and plus E3 cap times omega 1 A2 minus A1 times omega 2. So, what exactly happened? Okay, we have started with this. So, this term we are writing as 0. This term, if the vector is fixed, the case 1 we are taking where the point P is fixed. So, in that case this part is becoming 0 and only this part we were considering. So, in this part we need to insert the expression for d E 1 cap, d E 2 cap and d E 3 by d t cap. Okay. And procedure for doing the same thing. So, d E 1 by d t cap we were trying to find out. So, due to one rotational change we saw that this is the omega 3 is coming into picture here. Okay. So, the angle delta E by delta E 1 by delta t, okay, because of the rotation about the E 3 x, this will be omega 3 and it points in the direction of omega 3 itself. So, this vector becomes E d E 1 cap by d t, this you can write as omega 3 times E 3 cap okay, but here be cautious, this is only due to rotation about E 3 x. Okay. Then we have to take care of the rotation about the E 2 x. So, this thing we will be doing comprehensively in our attitude dynamics part. Okay. So, if we continue with this, okay, so with A 1 we can see that with A 1 ultimately the E 3 vector is manifesting. So, sorry, the vector is in the direction of the E 3 and omega 3 is manifesting. Sorry, this we write as, this figure has gone. Okay, let me make another figure here. This is your E 1 cap and this is your E 2 cap at time t, and this is basically due to the rotation omega 3 here, that it is changing in the E 1 E 2 plane, okay, and this we have written as delta theta. Okay. So, the change once E 2 approaches this you are writing as E 1 t plus delta t and this is E 1. So, this is your delta E 1. So, as this approaches this vector points in the direction of the E 2, not in the direction of the E 3, but the rotation which is taking place delta theta by delta t, this is in the direction of this is basically nothing but your omega 3. So, in the limit delta t tends to 0, Okay, this you can write as omega 3 in this place. Okay, so, therefore, the one part of d a 1 by, we had the first part d a 1 by dt times d e 1 cap by, sorry, this is a 1 times d e 1 cap by dt. This is the first part, plus the second part is a 2 times d e 2 cap by dt. The third part is a 3 times d e 3 cap by dt. Now, naturally from this place what we see, this part gets reduced to a 1 times omega 3, and the vector now it is directed along the E 2 direction. So, E 2 cap will manifest here. Okay. Similarly, if you give rotation about the E 2 x, we are giving positive rotation using the right hand rule. So, this is your omega 2 here, and then this vector, instead of now taking it up, we can show it going down. Okay, and let us say this angle we show it as delta phi. Okay, so, you can see that the rate of change of this delta phi, again you can write this as E 1 t, and this is E 1 t plus delta t. We are considering each rotation separately. Okay. So, if it rotates, this is your delta E 1 t, putting cap here. So, this vector which has changed, as we have discussed in the last lecture, this is nothing but your delta phi times E 1 cap t magnitude. Okay. So, this is the magnitude of this vector delta E t. Okay. And if we divide both side by delta t and let delta t tends to 0. So, limit delta t tends to 0, and here also take the limit delta t tends to 0. Okay. So, this will give you, this quantity is basically 1. So, this gives you d phi by dt, and this is nothing but here serving as the omega 3. Yes, in this direction this is serving as omega 2, not as omega 3. And what is the direction in this case is, here this vector, the rotation is taking place like this. So, this is the rate of change of this angle will be pointing in this direction, and this vector, the vector which has changed. So, this vector is associated with the direction as this approaches this place. So, this is in the negative direction of omega 3. So, we write here with the same thing, here you can write as omega a 1 times and then multiplied by omega 2 times omega 3, but with a negative sign. Okay. Now, you search for the expression that we have written for expanded expression we have written here in a 1 where it appears. So, look for that sign a 1 with omega 3, this is a 1 with omega 3, this is, and E 2 is here. So, this part is, you can see this is positive sign, and then you look for the a 1 omega 2 omega 3, a 1 omega 2 a 1 times omega 2 times omega 3, this is your omega 3, this is with a negative sign. So, this way you can assemble component wise each of them, and then combine the terms with E 1 cap, E 2 cap and E 3 cap together, and you will get this expression. And the same expression I wrote this in a one shot as d a by dt as omega cross a. So, here finally, this expression, once we are reducing it. So, we are writing as d a by dt in E 1, E 2, E 3, this will be equal to omega cross a if a is a constant vector in E 1, E 2, E 3 reference frame. So, the magnitude of the vector, this vector, the magnitude of this vector, this also becomes a constant in the capital E 1, E 2, E 3 reference frame, which is non rotating. So, you see this how important this conclusion is. So, from here what we get, that if the vector is fixed in magnitude, then simply the first part here vanishes and we get the only the second part as omega cross A. So, this gets reduced to omega cross A, but if this magnitude, the component of the A vector, it is a changing in the body reference frame itself. So, it will also change in the x y z reference frame, and I as I stated, the scalar change, the rate of the scalar as as it appears from a non rotating reference frame, it is the same as from the rotating reference frame, and therefore, in that case we can write dA by dt, the case 2 A is varying in this is case 2 varying in body reference frame, that is in E1, E2, E3. So, here in this case we can write this is dA by dt with respect to E1, E2, E3, small E1, E2, E3 plus omega cross A. In this case, as the rate of change of this appears from the E1, E2 reference frame. So, here you have these are the, in the case the vector A is changing in the magnitude, its components are changing. So, you just have to take the components of this, and the same thing has been written here in this format. So, here basically your dA by dt E1, E2, E3, this we are writing as A1 dot E1 cap plus A2 dot E2 cap plus A3 dot E3 cap. Okay, so, this is going to be the same as seen from the E1, E2, E3 reference frame, or either from the small E1, E2, E3 body reference frame. Okay, so, we have done a part which was very important for understanding further our derivations. So, next we go into sorry. Okay, so, here P is a point, and say this point O is the center of mass of this body. This is a point we have taken inside a rigid body, and even E2 reference frame is fixed in this, and this reference frame is rotating with an angular velocity of say omega. So, and this vector we have written as A. So, now instead of writing this as A, we write this as the rho, and the vector from this place to this place we write this as r, and the vector joining the point O prime and the point P, this we write as r. So, obviously, we can write r equal to r plus rho, and therefore, the rate of change of this in the E1, E2, E3 reference frame, this can be written as dr by dt E1, E2, E3 plus d rho by dt E1, E2, E3. Now, whatever the conclusion we have made in the last part, okay, so that applies into here this place. Okay. This is a vector which is being referred from this point to this point in the rigid body. So, this vector can be either expressed in the components of the E1, E2, E3 or in the body components. but here we will describe this vector in terms of the body components. Okay, so, r double dot we write this as left hand side E 1 E 2 E 3 this will be equal to r double dot E 1 E 2 E 3 plus d rho by dt. So, that we have written as we can write as d rho by dt as seen from E 1 E 2 E 3 reference frame and plus omega cross rho. This is the first derivative that we have taken. So, this quantity has been this quantity has been expanded and written in this format. This is the first derivative, only one point dot will come. This is the first derivative. Okay, next we take the second derivative. So, this we write as d square r by dt square, and this is with respect to E 1 E 2 E 3 reference frame. Okay. And here this we will write as r double dot E 1 E 2 E 3. So, naturally we need to differentiate this quantity here r dot E 1 E 2 E 3 plus this we will write as rho dot E 1 E 2 E 3 plus omega cross rho, and this we have to do with respect to E 1 E 2 and E 3 reference frame. So, expanding this part, because this is a vector, again r dot is a vector which is in the E 1 E 2 reference frame, and we are taking the derivative in that itself. So, it does not make any difference, we can directly write this as r double dot E 1 E 2 E 3 and plus d by dt rho dot. Okay, so, now this rho dot is a vector which was in E 1 E 2 E 3. So, we need to drop out this symbol here, this symbol the maybe this symbol we can take as E, and this symbol we can keep as capital E to abbreviate here in every place. So, here we can put as E and outside we can keep as E. So, this we can replace by E, and then of course, we have to write d by dt omega cross rho, and this is with respect to this E. So, we have r double dot E, this becomes now differentiate the quantity which is written inside rho dot as it appears here. If you remember from the last part as we have written, so this can be written as rho 1 dot E 1 cap plus rho 2 dot E 2 cap plus rho 3 dot E 3 cap, and plus the next term again we have to write. So, this term we can write as d omega by dt cross rho, this is with respect to E, and plus omega cross d rho by dt, this is with respect to E. Now, we have to take care of this particular part. Okay, as proceeding in the last part. So, we can write here directly as rho 1 double dot E 1 cap plus rho 2 double dot E 2 cap and rho 3 double dot E 3 cap, and this we are writing with respect to E, but this is also equivalent to writing it with respect to the small e as we have argued just before. Okay. Exactly we have done as for the A vector, we are doing the same operation here, and the other part of this can be written as rho 1 dot times d 1 cap by dt plus rho 2 dot times d 2 cap by dt plus rho 3 dot d 3 cap by dt, and this is for with respect to this capital E reference frame, and of course, this quantity we can write as omega dot, and this is rho, and the quantity which is present here, this is omega cross. Now, d rho by dt with respect to E we have already written as d rho by dt with respect to the small e, that is with respect to the body reference frame plus omega cross rho. So, now writing this equation here on the next page. So, we have R e double dot, which is the acceleration in the inertial frame. This can be written as R e double dot, and the term which is present here, which we have writing as A e. So, this term is basically the acceleration with respect to the body reference frame, okay, because as we have discussed, the time derivative of a scalar, it does not depend on the reference frame. So, like the temperature in a rotating reference frame, and so we have the temperature in a rotating reference frame. So, its time derivative, it will be same from a non rotating reference frame also. So, the time derivative does not get affected. So, we are taking here the time derivative of rho 1, rho 2 dot, rho 3 dot. Okay. So, here the E notation, which is for the inertial reference frame, we replace it by a small e to indicate this is with respect to the body reference frame, and therefore, we will use A e for this. So, we write here A e for this acceleration. Now, this acceleration, this you can write as omega cross rho dot, because as earlier described, this is E 1 cap, E 2 cap, and you are taking the derivative of this. So, we can earlier I have proved this, how to work out this. So, here you can replace this in terms of omega cross rho dot. So, once this is done, then the last this term is remaining omega dot cross rho, and then finally, we have this term here. So, this is your basically rho dot with respect to the body reference frame. So, we can write here omega cross rho dot plus omega cross rho, and now accumulating the terms together wherever possible, and this rho dot we can replace as V, and I can put a E to indicate this is with respect to the body reference frame. And this also we replace by V, and here omega cross rho. So, here this one and this can be combined together to give 2 omega cross V and plus omega dot cross rho plus so, this term is your Coriolis term, this term you can identify as the centripetal acceleration. Okay, for very simple cases you can check it. Say your omega you can write as omega times say E3 if you are writing this a very simple case. So, the omega cross rho and rho vector you can write as say again rho vector we describe as rho times E 1 cap. Okay, so, this will become omega times E 3 cap cross omega times E 3 cap cross rho times E 1 cap. Now, check from this place, this is omega square and rho 3 times rho 1, this is nothing but rho 2. So, this becomes E 3 cap times E 2 cap, okay, and E 3 times E 2 cap, and here we put the rho which is present here. So, this becomes omega square times rho and E 2 times E 3 times E 2, this is minus E 1. So, this is minus E 1 cap. So, basically what it shows that your rho vector, this is along the E 1 direction, you have taken from here that this is your rho vector. So, this indicates that this acceleration is directed towards opposite to the rho vector, that is directed toward the center of the point about which the rotation is taking place. So, this is basically your centripetal acceleration in inertial reference frame, and this is the Coriolis force that we call. But the Coriolis force, these are basically the Coriolis force, where you will be able to see it in the, if you are in a rotating body reference frame, and this is related to the angular acceleration. This term is nothing but your angular acceleration and this multiplied by rho. So, acceleration related to the angular acceleration, this term becomes. Okay. So, here we can so, first to show the effect of the Coriolis acceleration, we take the case of the earth and say this is the r vector, and here we have the body reference frame which is E 1 directed radially outward, E 3 cap, E 1 is in the east direction and E 2 is in the north direction. So, earth is rotating about this x with capital omega. So, here we can show that this is the angular velocity of the this body frame. Now, I will take this quadrant only and show this picture here is separately. E 3 cap, E 2 cap, this is your lambda. So, this will be lambda this is the angular acceleration vector, this angle will be lambda. So, in the E 2 direction thus capital omega vector, this you can write in the body reference frame as capital omega cos lambda times E 2, taking component along this direction and plus sin lambda is component along this direction multiplied by E 3. Now, suppose the wind is coming from the north pole, this is your north pole and this is below the south pole is there. So, wind is coming from this direction. So, here I can show that the wind is in the direction V, I can write as minus V times E 2 cap. So, the Coriolis term that becomes 2 cross omega cross V. So, this is minus 2 times omega, from here we can insert. Okay. So, this is capital omega cos lambda E 2 cap plus capital lambda E 3 cap cross V, which is minus V times E 2 cap. So, this implies this quantity becomes minus minus, this gets plus, and we can write 2 V, okay. E 2 cross product, this will vanish here, we can put the cross product here in this place. So, E 2 vanishes and we have to take the cross product of this. So, E 3 cap cross E 2 cap, this is E 1 cap minus, okay. And then we have to take care of this capital lambda. So, capital lambda we can put here, and then we have the sign lambda, okay. And this is with a minus sign. So, what it gives, that minus 2 times omega cross V, this is your 2 V capital omega sin lambda times C 1 cap. So, this Coriolis acceleration in the body reference frame. So, your body reference frame is shown by this green lines. So, it is acting in the direction of negative E 1 direction. Okay. So, it is acting in this direction. So, this is the east direction, this is your east, this is local vertical, and here this is your north direction. Okay. So, at any point we identify like this, this is your north direction. So, east north, and this is vertically up. So, this is the west direction. So, this we can show here as the west. So, if the wind starts from this direction, so it will turn towards the west, okay, and that is what happens. So, in the northern hemisphere you will see that the, if you read your geography book, you will see that the wind which starts from the north pole, okay, so they turn towards the west. So, this is your north pole and this is the south pole, this is equator. Okay. So, they will turn toward the left, and this happens because of the presence of this Coriolis acceleration. Okay. So, I have shown the Coriolis term here, then I have shown this centripetal term here, and this is basically due to the increase in the angular velocity. Okay. So, remember that in the body reference frame, once we take it to the body reference frame by writing I can write this as E equal to R e double dot minus R e double dot minus 2 times omega cross V minus omega dot cross rho minus omega cross. So, once you are looking in the body reference frame, so this term which is present here, this is basically your the negative term that I was showing, the Coriolis term, and this is your, now the centripetal term we will write this as, so this has the centrifugal force, because in the body reference frame what you will feel is the centrifugal force. So, this is gets the centripetal term once we change the side, once we are looking from the relative to the body reference frame. So, centripetal will appear as the centrifugal one, and this is basically related to your tangential acceleration because of the increase in the angular speed. So, we have to determine this omega dot cross rho term. So, we can take of body reference frame E 1, E 2, E 1 cap, E 2 cap, E 3 cap. Okay. Now, omega is a vector which is directed along this direction, okay. And this vector is, because we here we will take a simple case that omega is directed along this. So, we can write omega equal to omega times E 3 cap. So, we can write d omega by dt, this is equal to d omega by dt times E 3 cap plus omega times d E 3 cap by dt. Now, we can look from this place that here d E 3 by dt cap, because the rotation is taking place about this body x only. So, there is no change in the direction of the E 3 cap, unlike the earlier one. So, this we can drop it out, this becomes 0, and here we can write d omega by dt equal to omega dot times E 3 cap. So, this term gets reduced to omega dot cross rho, this will become omega dot, and rho is basically we are taking here in this direction. So, this is your rho vector. So, omega times E 3 cap, and rho vector is rho times E 1 cap. So, this becomes omega dot rho, and E 3 cross E 1, this is nothing but your E 2 cap. So, now you can see that omega dot rho times E 2, this is representing a vector in the direction of E 2. So, E 2 is in this direction. Okay. So, if your this is the vector, and if this is rotating, so this is pointing that this acceleration is directed in this direction. And the same thing if you look from the body reference frame. So, the negative sign will come into picture, and you just have to put a negative sign before that, and this gets into the opposite direction. So, in the body reference frame it will appear in the opposite direction. So, thus we conclude this part on the kinematics of particle. Okay. In the next lecture, we will start with the particle dynamics. So, in the particle dynamics, in the space dynamics, we are concerned with the heavenly bodies. So, we will look into the dynamics of the, basically we are going to work with the dynamics of the heavenly bodies or the satellites. So, when the earth is there, around the earth the satellite is moving and there is some other planet. So, we will explore all these things in the future lectures. So, we stop here. Thank you very much.